I'm going to talk about data-driven challenges, and also we'll talk about one of the solutions that industry is adopting to overcome these challenges with generative AI. Let's get started. Before going deep into the generative AI challenges and vision, let's take a step back and then see how far we have come. It looks like ages, but BERT was introduced by Google in 2018, and then BERT was a game changer in how machine understands the language. It's a bidirectional training model. It was pretty groundbreaking at that time. Um, BERT could understand the context of the word by looking at all the surrounding words, basically understanding the context. And then imagine having a conversation where you understand each word not just by itself, but like in the context of everything being said around it. That's what BERT did for natural language processing. It was a big leap forward in answering like question answer questions and then language inference, uh, and then capturing the nuances of the individual languages of humans, right? And then moving to GPT-2, which was I'm skipping minor ones in between. I'll just cover the major ones. Um, Now moving to GPT-2, this was released by OpenAI in 2019, building on what BERT has achieved. GPT-2 shifted focus to something else, like generative capabilities. While BERT was good at understanding the language, GPT-2 excelled in like creating it. With close to 1.5 billion parameters, it could generate text that was coherent and contextually relevant. And then then coming to GPT-3, this was, I think, in 2020. This was massive in both size and impact because, as I was saying earlier, GPT from GPT-2 to 3, the number of parameters exploded. GPT-3 has close to 175 billion parameters. With the increase in size and complexity, GPT-3 took the generation to a new level. It has improved contextual understanding. It is sophisticated and more nuanced. Could generate text and uh, more data, incredibly human-like across various styles and formats. Uh, and then finally coming to GPT-4, this is the latest generation. Uh, while we don't know the exact number of parameters, it's significantly larger and more complex than GPT-3. GPT-4 takes everything a notch higher. It's better at generating coherent texts, and the new multimodal ability. It just doesn't, it just don't understand text. It can also process images. If you have tried the latest Chat GPT, the paid version, it has GPT-4 enabled, and then basically you could give in PDFs or images, and then it could basically understand your image, and then say you can give them a flow diagram and then ask what's going on or what's wrong. GPT can understand that. It's pretty sophisticated and then creative in that way. So this is where we are. Let's see what is the future that's coming ahead. So first thing is these models uh, need to generate their own training data. Think of it as an AI engaging in some kind of self-reflection, right? Using what it knows to create new content. This self-improvement method is showing promise, especially in languaging tasks. Imagine an AI that asks and answers its own question, then picks the best response to learn from it. It's a big deal because it helps AI bootstrap its own intelligence, addressing the potential shortages of text data for training. And the next big thing is fact checking. Uh, we have models that can fact check themselves. This is a major step towards addressing the issue of AI generating misleading information. Efforts are being made to enable AI to pull information from external sources and cite references so that the yeah so that the model doesn't give like uh, egregious or misleading information which could be harmful in some ways. And the next big trend is massive sparse expert models. Yeah, this is another trend. Unlike traditional models that use all the parameters for every input, sparse models activate only the relevant parts for the specific query. This makes them larger yet more efficient. Think of them as a team of specialized experts, like each handling a different topic. They're a game changer in terms of efficiency and interpretability in AI. The next big thing is chain of thought prompting. This is about improving AI's reasoning by making it think out loud. It's especially useful for complex multi-step problems, offering a, a chance to look at how AI reaches to a conclusion. While it doesn't solve all challenges in AI reasoning, it's a significant tool to enhance clarity and then reducing errors. This is specifically helpful when debugging to know why something was shown as a result or an answer, and then going back to its sources. And the final one is better fine tuning and alignment. This is crucial for like tailoring the AI to specific needs. For instance, ChatGPT's training uses reinforcement learning from human feedback, where human feedback shapes the AI's learning. As these models grow, the ability to fine-tune them for specific tasks become increasingly important, making them more versatile and effective across different fields. Yeah, this is the future, but the next thing is very, very important. What are the challenges? First, let's talk about addressing hallucinations. Many might have heard about this term hallucinations. This is basically, say you ask a question to ChatGPT, if it doesn't know anything, it will start giving you garbage, and then it will start making up things. So this is about developing methods to both reduce and then measure instances where model creates inaccurate or nonsensical information. It's a big challenge, but it's essential for reliability of LLMs in real world applications. Efforts are being made to refine algorithms for better understanding of the world and to create metrics that can quantify how often these hallucinations happen. This is to enhance basically the trustworthiness and utility of LLMs in various domains. Now, the next big challenge comes to understanding the context. Context is crucial in understanding questions accurately. Take, for example, if you ask what is the best, say, a restaurant. Now, ChatGPT say if it doesn't or LLM if it doesn't know about your preferences, then there is no way that it could answer that question correctly. It could just give some answer, but it won't be the correct answer. So to solve this context problem, industry has come up with something called retrieval augmented generation. We'll speak more about it in the next slides, but what it does is it basically um, harmonizes both the context data and then the results from LLM to generate a best possible answer. And then the next challenge is uh, making LLMs faster and cheaper. Uh, if you have used the OpenAI or any other LLMs, it's incredibly slow, to be honest, because in the world of things moving in microseconds and seconds, it takes a couple of seconds to get an answer, and then on top of it, systems have to make it make more enhancements to it or make a decision how to use that response from LLMs. So another goal is to make these LLMs faster and cheaper. As the models grow in complexity, it's crucial to reduce operational costs and increasing processing speeds. This involves innovation in both model efficiency and hardware optimization. Talking about making them cheaper, just for context, to train one LLM model, today it costs like close to $3 to $4 million. So it's impossible for smaller companies to even think of training their own models. So the aim is to make LLMs more accessible for everyone, from small developers to larger enterprises. The next big challenge is GPU alternatives. As you might have already aware of this, currently there is just one big market leader, NVIDIA, who is providing GPUs. So, and then given their scarcity and the cost, high cost, and also the energy consumption, alternatives like TPU, which is pioneered by a few cloud providers, and then FPGAs or custom AI chips are being considered. The reason is the reason is there are some tasks in the LLM uh, flow where they don't need GPUs essentially. They could be swapped with TPUs or other AI chips, which could provide a cost-effective solution for processing LLMs, which is uh, especially important in like resource constraint environment, and also to bring down the cost. Uh, yeah, and the last thing is agents, making these agents more and more usable. This means like to improve the decision making capabilities, ensuring they can accurately interact with various systems and interfaces. Like say you can think of an agent to write a Google Doc or make a Google presentation for you. This will basically enhance the usability in, which is key to integrating these agents into like practical applications like healthcare or personal assistant or customer service. These are the challenges that the industry is facing today. Uh, Now let's like explore some solutions. There are a couple of solutions that we can talk today, but I'll go deeper into one context generation solution in the next slide. Just to give an idea, uh, these are some of the solutions that industry is uh, using today to make LLMs faster and cheaper. First one is quantization. This is like reducing the precision of numbers used in the model. Think like using 32-bit and then 16-bit. It makes the models smaller, speeds up the computation, and in turn makes LLMs more efficient and less demanding. And the next one is knowledge distillation. Here we train a smaller model. Uh, Say you can think that as a student to mimic a larger teacher model. The student model is lighter and faster, making it more practical for real world use without losing much performance. And low factorization. This method tackles the complexity of uh, weight matrices in neural networks by approximating large matrices with lower rank one. We basically effectively reduce the number of parameters. So once the number of parameter comes down, it will be smaller, faster, and demands less computational power. And finally, pruning. This involves removing parameters from the network that aren't crucial for its performance. It's like trimming the excess to make the model leaner. Pruning leads to models that are not only smaller and faster, but also memory efficient. Together, right, these techniques are crucial in reducing the complexity and financial limitations of LLMs, making them more accessible. Now, let's tackle a major challenge in AI, context construction. Often, these large LLMs lack context. Like, say, when a customer support engineer generates an email, if you ask LLM to help with writing email, LLM doesn't have any context on that email, so LLM cannot help. This is where like retrieval augmented generation, also known as RAG, comes into play. It's revolutionizing how we use AI to knowledge-based tasks. Now let's try to understand the flow and how this works. The first step is indexing. This is like, say you have a library of all the business documents. This could be technical, customer support, knowledge, anything. The goal is to make this information AI accessible and usable. First, a data loader reads this text and breaks it into manageable chunks. Think it of think of like uh, making these information into smaller embeddings, and then the embedding model takes these chunks and then turns into numerical representations, kind of like fingerprinting each doc. These embeddings are now stored in a vector database, which is all about fast retrieval based on. So vector DB is basically used to say fetch similar documents. Say for example, you uh, try for searching for a food, it's more likely to be associated with say restaurant. So vector DB will basically retrieve all the similar documents which are related to food. It will not just look for the actual word food, but it will also look for something similar like say a restaurant or a hotel or whatever. All those similar words that come in similar context. So once this data is indexed, this happens in batch and in offline, or whenever a new document is added or made edits to. The next step is querying. Say when a customer or say LLM tries to call goes to LLM. Before that, we ask a question to vector DB. The question is then converted similarly how document is converted to embedding. We convert the question also into an embedding. Then the vector database, we go ask that question using the embeddings. And then vector database basically retrieves all the similar documents. The system only, then system basically gives the relevant documents from vector DB, which is then passed along with the question to LLM. Now what we're doing is we basically not only gave the LLM the question that customer is asking, we also gave it the relevant information. So now with the context provided by user and the question that the user is asking, LLM uses the relevant chunks to generate response. That's informed by the knowledge base. So yeah, you can think of like a customer scenario where like say if I just ask the question, how do I reset my password? Now the customer or the LLM doesn't know what is my system, and then he doesn't know how to reset password in my say an application. Now say we have indexed the previous instances where this has happened or previous cases where this has happened, and then the solution that a customer agent has provided. Now LLM can intelligently look at those previous cases along with the question that the user is asking and then give the solution instead of just giving a solution based on whatever knowledge that just the LLM has without knowing about the customer specific system. I think this approach uh, doesn't just offer quick and accurate responses, it also learns over time, significantly improving the experience.